You're telling me this big old circuit board doesn't have a big enough diode for me? D671. Let me try that. Did I already try that one? Yes, I did. Grr, they're all too weak, man. I need a big, bad boy. I need a gangster diode. I need a diode that ain't afraid to lay the smack down. I need a diode on steroids. What amps diode do you need? Let me look up the amps. So we're looking at 500 volt 8 amps. Uh-oh. Now I'm confused. Sorry, guys. It looks like I just ran into a problem here. It's supposed to be 100 amps. A 100 amps, 18 volts. Alright, I'm confused. The MOSFET leading into it is dealing with an input of 155 volts, switching that on and off. Okay, so he can be 8 amps, that's fine. He's gonna send a ton of electromagnetic force into the inductor because he's such high voltage. When he switches on, not much current has to pass through him in order to charge the inductor to full. When he switches off, the inductor does the rest of the work. The inductor is going to be the one outputting a lot of current in a lower voltage. So he'll switch on at a low current, high volts. The inductor will quickly rise up in voltage due to the high voltage source. The source shuts off. The inductor is now at the set voltage of 18. It didn't take much current to make that happen because of such high potential going into it. But he rose up to 18 volts very quickly. Now when he blows his load, that will run at a high current. 100 amps. And that 100 amps is going to go through the system and then come back through the diode and into the rear of the inductor at 100 amps. So that diode needs to be like a very high amperage diode. You act like 100 amps is a high amount of amps at 18 volts, but it's really not. A cordless drill pulls 70 or 80 amps. That's just one motor. If you combine that with 10 amps to charge all the batteries, the 5 battery cells, at around 2 amps each charge rate, you know, you're probably looking at 30 amps my system will draw. So I would say more like 30 amps is the total draw I'll be putting in. But I still wanted it to be capable of 100 amps in order to create a model of a buck converter that can output 18 volts at 100 amps. That's an impressive, you know, throughput. It's a high wattage buck converter. I want to have that ability, even though my system won't actually require that. I want it to be capable of putting that out if my system were to be upgraded, because this is a prototype of the power supply buck converter that I'm going to be using for the robot. Let me look up like a really powerful diode just to see like what's out there, you know. At least like a 30 amp diode. Three amps, 1000 volts, super cheap. 1 amp, 1000 volts, super cheap. Okay, so those are popular. That's cheap means popular. 10 amp, 1000 volt. Okay, 10 amps is not bad. It's starting to get up there. $10 amp, 1000 volt seems pretty dang popular. In fact, I ordered these guys already. But I'm looking for a high amp diode now. I just prefer to look at what's popular under diode. It's sorted by popularity, so I want to go with the popular one. It's usually less expensive. Alright, I'll keep that in mind, but I'm sure I'll have no problem finding one sorting by popularity, just scrolling through. I prefer to actually read through this stuff. I'm not in a big rush. I want to see like a lot of examples of different diodes. I'm learning just what is popular in general. I'm looking at the sales numbers. I'm able to compare and gain a feel for the diodes market. I've noticed that sometimes my designs are proven flawed when the part I'm buying is much more expensive than the part should be, and it's probably because I'm using a design that's never done because I made a mistake. So I like to compare all the prices of similar items and then find out if I'm using a part that's popular. That probably means my design is probably a common-ish design that's reasonable. It's kind of a little hint that I'm on the right track. Dang! 70 amp, 100 volts. What? And they're popular. Look at that. Oh, snaps! Guys, we can use a MOSFET instead of a diode. Oh! Wait, let me picture why. Okay. So let me explain this. This first MOSFET, 500 volts, 8 amps. It's going to be sending through 155 volts at... I mean, how many watts are we producing here? Well, let's just say 75 amps, right? Times 18 volts. 1300 watts. Now, it's got 155 volts going in. So, 1350 divided by 155 equals 8 amps. Yeah, it'd have to be a little less than that. So we'd have to go for like 900 watts. So let's say, actually it's going to be more like 60 times 18, which is 1080 watts. So 60 volt, or 18 volts, 60 amps. If we pull 60 amps, would give you 1080 watts, and then divide that by the 155 as the input voltage, and you get 7 amps. So that's within the acceptable range of the 500 volt 8 amp MOSFET we're using as our switching MOSFET at the start of our buck converter. So we can pull as high as 60 amps from this one buck converter. We have to create a second buck converter if we wanted to go for higher wattage. But 1000 watts is actually really good because the wall outlet of a house is only 120 volts times 15 amps, 1800 watts. You don't want to be pulling more than 1000 watts anyways, because that would blow your fuse if anything else is running on the circuit. So I'd rather not even have something that high. So that's plenty. 60 amps at 18 volts would be plenty, plenty, plenty. Plus, I mean, my motor probably will only pull 15 amps tops. I mean, it might pull 20 on the vacuum. And then the batteries at peak charge rate might pull another 8. We're looking at like 28 amps total anyways. 28 amps at 18 volts is about 500 watts. So that's nothing. So this MOSFET's going to be fine. Now, the power coming out of this inductor is going to be coming this way. It's going to be going through the circuit and coming back eventually. And when it comes back, it's going to go up and back into the rear of the inductor. So it's going to go through, around, and back up. Assuming this is off, this thing's going to just keep feeding. Okay, and then this one's going to feed when this thing's dead, once it's emptied. It's just going to help out and smooth out the voltage. The voltage won't drop when this thing starts getting low. This is going to drop voltage over time as it outputs, so then this thing will help out. So the two of them provide voltage, and the voltage should be kept pretty steady thanks to the capacitor. Well, I think what I just said is right. This is supposed to smooth the amps. This is supposed to smooth the voltage. But bottom line is this thing gets charged up and it shoots its load to the right and then comes back up and in. So this diode allows the return path back to the inductor when it discharges, but prevents the inductor from discharging in a counterclockwise direction. Okay, so the inductor could discharge like this and send it up the ground. Bottom line is this: when this one's open, we don't want this shorting out our system. So this one's closed. When this one closes, this one can open. It needs to open pretty quickly as well. I'm thinking of using, well, let's see, it'd have to be a 18 volt. Oh shoot, we've got plenty of MOSFETs that can handle that. We just don't have any inductors that can handle that. I mean, any diodes that can handle that. I mean, you need a $5 diode to do it. I just assume use a MOSFET for it. We would want like a 20 amp high volt, 20 volt high amp MOSFET. So we've got here, let's see, that's not a good one. 60 volt 5 amp, no. This has got to be it. Yes, 55 volt 110 amp. This is an IRF 3208 MOSFET type N. This would be a low side switch because it is grounded. And we'd be putting it in place of our diode and our buck converter. I read about doing that. It is a little more risky, but YOLO, and we can implement right away. I want to read about the risks involved. This is a totally new design change being made for one reason and one reason only, and that is we don't have a diode that can do this. It's not a popular diode, it's not something readily available, and so we're going to replace this with an N-channel MOSFET. Okay, so I'm going to go into the Wikipedia article on buck converters, and I'm going to read about the option of using a MOSFET instead of a diode. Now, one of the great advantages of using a MOSFET over a diode is you gain a lot of efficiency since the diode has a voltage drop, and just the difference between a Schottky diode and a normal diode can give you like a 20% efficiency boost, with the Schottky diode having a lower forward voltage drop. So the diode is really the biggest herder of your efficiency in this case. So just using a switch, having it wide open, is a lot smarter move. You just got to make sure your timing is right.
Now, next, let's control the switch with a high-frequency pulse-width modulated signal with a duty cycle of 50%. This will give us a square wave that's 10 volts half the time and 0 volts half the time. Now let's add an LC low-pass filter. The inductor resists sudden changes in current, and the capacitor resists sudden changes in voltage. The combined effect is that our LC low-pass filter averages out the square wave, and we get 5 volts of relatively steady DC on the output. Now, unfortunately, if you build this in real life, this will happen.
See guys, that's what I'm talking about.
But why? Well, let's say the switch is closed, and our power supply is delivering some current. This means that current is flowing through this inductor. Now let's open the switch. Since current in an inductor cannot instantly change, this means that current is still flowing through the inductor, but this side of the inductor isn't connected to anything. So you get this huge mass of electrons building up here, creating a massive negative voltage spike. This voltage spike can reach hundreds or even thousands of volts, enough to blow up any switch you connect here. If you want more detail about this phenomenon, check out my video on inductive spiking. In that video, you'll learn that the solution to the problem is to add a diode. With the diode in place, now whenever you open the switch, current can flow in a nice complete path, and the voltage after the switch barely goes below 0. This is the classic buck converter configuration, and you can use this basic circuit to step high DC voltages down to lower DC voltages in a much more efficient way than linear regulator.
What we're about to do right now is sick. replacing this diode with another MOSFET. But I just want to read about what the pros and cons of that are. Because this diode, we don't actually have one. I'm not going to wait to order one. I'd rather use parts I already have. That's always my goal, is try to use parts you already have. Since there's always more than one way to do things, I look for the way that I can do it with parts already on hand. I don't like ordering parts unless if it's absolutely necessary. Although modern buck converters frequently replace the diode with a second transistor, baby!